Chapter 8.6 is going to look at anaerobic respiration and how it differs from aerobic respiration. Remember, in the earlier sections, we talked about how aerobic respiration requires oxygen and anaerobic doesn't. The only step that occurs in anaerobic respiration from our previous four is glycolysis, the first step. Remember, again, that's because glycolysis occurred very early on in life. And oxygen was very low in the atmosphere. The levels of oxygen were very low, so that process had to evolve around an environment that didn't have oxygen. So glycolysis is the first step. It's the only one that's anaerobic. Remember that the last step is the only one that really uses oxygen, which is the electron transport chain. But since we have to have a bunch of NAD and FAD readily available for the prep step, for the prep step, the Krebs cycle, and the electron transport chain. Without the oxygen, those second, third, and fourth steps won't occur. So we don't make a lot of ATP. So the whole point of glycolysis is to break down glucose and produce ATP. We also need NAD for that. We need to make it into NADH. However, if we have a low amounts of NAD and we don't have any of the NAD left, we can't go through glycolysis. So all of the NADs will be NADHs during anaerobic respiration, or at least the beginning of it. What happens is we have to oxidize NAD or I should say NADHs to make them NADs in order for this process to continue. So again, you can see we need the NADHs and FADH2s to come down here to the electron transport chain. However, if all of these NADHs and FADH2s are filled, then we don't have any NADs or FADs. Imagine this is like a city with a bunch of taxis that are filled and they can't unload their passengers. We need more taxis to be emptied, like NAD and FAD. So what happens is we have two types of anaerobic respiration. One is called alcoholic and the other is lactic acid fermentation. Alcoholic fermentation is how you make your breads, your wines, your beers. Lactic acid fermentation is how we specifically go through anaerobic respiration and we produce lactic acid as a byproduct. Now, again, this produces a small amount of ATP, but at least a little bit of ATP is better than no ATP. Here are the two types of fermentation. You can see here we're using NAD and making NADH. And if we want this process to occur, we have to make more NAD. So what NADH comes down here is it oxidizes and becomes NAD. That reduces acetaldehyde here. And it's going to change it into something called ethanol. This is what is alcohol, and this is what are in your beers and your wines. Actually, a little bit in your breads as well. Now, you can't really get drunk off of bread, of course, but alcohol fermentation does occur in breads. Now, whenever we oxidize NADH, it becomes NAD, allowing it to further this process. So the whole reason we have our anaerobic respiration is to oxidize NADH to make more NAD to come up here and keep this process going. And remember, a little bit of ATP is better than no ATP. This is, again, the same thing with animal fermentation, which is lactic acid fermentation. The same thing occurs here, except we change pyruvate not into ethanol. We change it to something called lactate or lactic acid. This allows NADH to become oxidized, making it NAD, and coming back here and furthering this process. So another thing that happens when we want to produce ATP and we don't have any glucose is we start breaking down fat molecules. And we remember this from chapter 3 when we talked about triglycerides. We have our glycerol molecule here and we have our fatty acids. The really cool thing is this glycerol can be made into something called glyceraldehyde 3-phosphate. That's at G3P that can go into glycolysis. These fatty acids, why they're really high energy molecules, is these can be broken down to acetyl-CoAs. If you remember acetyl-CoAs, those are the molecules that go into the Krebs cycle. So without glucose, you can fuel the Krebs cycle, which produces a lot of the NADH and FADH2s and even a little bit of ATP itself. So we can keep your cellular respiration going without glucose. We just have to start breaking down triglycerides here. Now, in the opposite kind of thought process or the reaction, if you have a high amount of carbohydrates, so like I ate a pizza this weekend, I had half a pizza by myself, probably wasn't the best idea, but I ate a lot of sugars. What happens is your body can't use all those sugars, and they can't even store all those starches and sugars and reform them into like glycogen for the liver for long usage. So what happens is your body starts taking those carbohydrates and starts making them into fatty acids and starts making triglycerides. So in the opposite reaction, if you start eating too much sugar, what your body does is it starts storing it as fat, and that's how people can gain weight is if they eat a lot of like high sugar like food. You can see here, same thing that we just talked about. Those I'm sorry, over on this side, these glycerol molecules can fuel glycolysis. Those fatty acids then can fuel acetyl-CoAs. However, the opposite reaction can occur where the acetyl-CoAs can come back here and form the fatty acids and form triglycerides, which is fat. Now, another place where you can produce energy from another molecule is like your amino acids. Some of your amino acids can be used as energy. So you can get some energy from a protein because they can be broken down differently and kind of transferred either into make pyruvate or acetyl-CoA, which goes into the Krebs cycle and fuels this process.